Friends, we have talked about hypothesis testing, and I gave examples mostly from non-parametric tests. Now, in this lecture and the next lecture, we will talk about two parametric tests. One is T and another is F. And in this lecture, we will show what T is, what is the probability density function of T, for what kind of hypothesis is T used, how is T applied, and what are limitations or what care has to be exercised in applying T test. So, to begin with, what is test? To test a hypothesis, we focus on some sample statistic. Now, the sample statistic has certain properties. It must be based on, or it must be a function of sample observations. We are testing a hypothesis based on a data set which is the product of a particular sample. This test must have a known probability density function. You cannot have a test. There are so many functions of observation, so many functions of data. All of them cannot be called statistical tests. Only those functions of observations will be called tests which have a known probability density function. And this probability density function depicts the probabilistic behavior of the function from one sample to another. Some examples of such tests are T, F, Z and chi-square. T is also called student's T. Then we fix probability of type 1 error alpha. So, once a test has been identified, we fix what type 1 error we are willing to tolerate. Usually, this alpha is fixed at 0.05 or 0.01 or 0.001, mostly at 0.05, which means that there is a 5% chance that the null hypothesis may be right, but we are rejecting it. Then find out what are the tabulated values of that test beyond which this much area 0.05 or 0.01 or 0.001 area lies. Calculate the test statistic for the sample and compare your test statistic with the tabulated values of T for 0.05 or 0.01 or 0.001. If the calculated value of test statistic, it may be T or it may be F or Z or chi-square, is less than the tabulated value, beyond which alpha percent area lies, then you are not going to reject null hypothesis. And if your test statistic falls in the critical region or its value is more than the tabulated value of the test for alpha percent type 1 error, then we reject the null hypothesis. This is the rule which we follow in all hypothesis testing. Something about nature of T distribution. Friends, T distribution is a symmetrical distribution. It has mean 0, and because it is symmetrical and it has mean 0, so its mean, mode, median all are at the point 0. And a parameter of T, an unknown constant of T would be nu. This nu defines the whole shape of the distribution. Nu is the parameter unknown constant and it is called degrees of freedom. For degrees of freedom nu, this f t nu probability that the random variable t takes a value t. Actually, since it is a continuous distribution, it will be more proper to write dt here and dt here. But since I just wanted to show what is the expression of probability density function, I have written it like this, that f t nu is gamma nu plus 1 by 2 1 plus t square by nu minus nu plus 1 by 2 and divided by square root of nu pi, pi is 22 by 7 multiplied by gamma nu by 2. Okay. Nu is called the degrees of freedom and the values of t vary from minus infinity to plus infinity. T can take any value from minus infinity to plus infinity. But as we have seen in the normal distribution, most values of t would be concentrated around mean and it is unlikely to get a value more than say 5 or 6, very unlikely. Probability of getting a value more than 5 or 6 or less than minus 5, minus 6 is almost 0. So, it is only in theory that t goes from minus infinity to plus infinity, but in actuality most values of t are concentrated around mean. Applications: t-test is used for significance of population mean and proportions. It means that the null hypothesis would be mu equal to mu 0. Mu is the mean of the population. For testing mu equal to mu 0 or for testing that pi is pi 0 or p is capital P, small p is capital P, means capital P takes a particular value, say p 0 or p is 0.5 or p is 0.7. For those kinds of hypotheses, t-test can be used. When you are testing that the value of mean or value of proportion in the population is this. T-test is also used for testing differences in means in case of independent samples and also for differences in proportions. You can make a null hypothesis that the difference in population means for two subgroups is this, or the difference in proportions of certain kind. Say you can hypothesize the difference in proportion smokers between urban and rural areas is this. T is also used under method of paired comparison, like before and after. You take a sample for experimental purposes and another sample for control and do an experiment in the sample and observe the behavior of sample respondents and compare it with respondents in the control group, and you can apply t-test for this kind of paired comparison. You can apply t-test for testing significance of correlation coefficient. When I was talking about correlation coefficient, I showed how the null hypothesis that rho equal to 0 in the parent population from which the sample has come can be tested. There we use t. T is also used for testing regression coefficients in bivariate regression, in multiple regression analysis. For testing partial regression coefficients about which we talked in the previous lecture, we can use t test. I actually showed how the value of regression coefficient divided by standard error of regression coefficient is distributed like t, and this t can be used for testing the hypothesis that beta equal to 0 or beta 1, beta 2, beta 3, they are all zeros in multiple regression. T is used especially when the sample size is small, when the population variance is not known, and this sample size is small property. This is because when sample size is large, above a certain value of sample size or above a certain values of degrees of freedom depends on sample size, and the t distribution starts behaving like a normal distribution. I will show you a t table, and you will find that after degrees of freedom 30, the values of t become very similar to values of z. T is also used in those situations in which the population variance is not known. So, if you are testing the null hypothesis that mu equal to mu 0 or pi equal to pi 0, mean or proportion, and you know the variance of the population, then you can use Z test. But if the variance of the population is not known and that is itself estimated from the sample data, then you will apply t test. For large sample and known variance, normal Z test is preferred over t, although it does not make much difference whether you go for Z or for t. The reason is that for large values of n, from which degrees of freedom of t is derived, t tends to behave like a normal distribution, and this is shown by this graph. You see this blue color, this probability density function is the probability density function of a normal distribution. It is written Z distribution, standard normal distribution. Standard normal distribution has mean 0, variance as a measure of spread as 1, and the shape of the density function is like this. For t distribution with n or sample size smaller than 30, 5, 10, 20 like that, the t distribution will look like this distribution. This is the distribution of t for n equal to less than 30. Actually, as n starts increasing, this t distribution is a platychotic distribution, because it is less peaked than the normal distribution. This platychotic distribution moves towards normal or mesochotic distribution as n increases. So, you see that when n is close to 30, this probability density function of t is moving towards the normal distribution. It is also platychotic as compared to this normal distribution, but as n increases, the t distribution becomes as peaked as a normal distribution, which also means that its spread or variance starts decreasing. You have largest variance for small values of n, and as the value of n starts increasing, the spread or variance of t distribution starts decreasing, and for more than 30, n equal to a value more than 30, t distribution will become exactly like a normal distribution. This Z standard normal distribution, it will have mean 0 and variance unity. although we have discussed this meaning of statistical significance, but again to clarify on the matter, the calculated value of t is compared with the tabulated value of t for a fixed alpha. Sometimes values significant at 0.05, I said that alpha is conventionally fixed at 0.05 or 0.01 or 0.001. So, values significant at 0.05 are shown with star. Those significant at 0.01 with double star and those significant at 0.001 with triple star. So, those values of correlation coefficient, for example, which are highly significant, which are significant even at 0.001, means for which alpha or p value is less than 0.001, they are shown by triple star. Values which are p values when they are less than 0.01, but are more than 0.001, they are shown by double star, and values which are less than 0.05, but values which are less than 0.01 and which are more than 0.01, they are shown by single star. So, in this way we make a distinction between significant, more significant and highly significant. Do you remember that lower is the value of alpha, higher would be the value of beta. So, that means for values for which alpha is less, in place of 0.05 you fix it at 0.001, then the beta or probability of accepting a false hypothesis or alternative hypothesis will increase. Both the errors cannot be minimized simultaneously, and if beta increases, then the power of the test, means probability of rejecting a false hypothesis would decrease. Low alpha, more beta, less power, less probability of rejecting a false hypothesis. This is how alpha and beta are interpreted. Look at this distribution. Imagine that this is the distribution under null hypothesis, such as rho equal to 0, and this is the distribution under alternative hypothesis, that rho is not 0, it is more than 0. It may be fixed at 0.1 or 0.2 or 0.3. So, this distribution, otherwise identical with this, is shifted towards right hand side. And now imagine that you fix alpha at 0.05 and the t value is this. So, this area is 0.05 and this area falls under the first distribution, the distribution under the null hypothesis, that rho equal to 0. This is the probability that the null hypothesis might be true, but you are rejecting it, because theoretically speaking values of t go from minus infinity to plus infinity. Any value is acceptable. A t value can even take a value of 50 or 100 or 300, but the probability is small. Actually, the probability of getting a value 3 or more itself is minimal, very close to 0. That is why we ignore it. So, this area is 0.05. For this area, the area under the probability density function of alternative hypothesis, t distribution, this is t distribution under alternative hypothesis. So, what is this yellow area? This yellow area is the probability of accepting the null hypothesis, because this is on the left hand side of this point. So, you are accepting null hypothesis, but it is possible that these values are part of distribution under the alternative hypothesis. It is a matter of possibility. No? So, this area while this area lies under the first distribution also, this area and some more area is part of the second distribution also. So, there is a probability of accepting a null hypothesis when the alternative hypothesis is true. This area is called beta, and for alpha equal to 0.05, the point will be fixed in such a manner that this area is 0.05, then this area is according to this graph, this area is 0.3628. Now, imagine that you reduce your alpha to 0.01, you move towards right hand side of this point. What will happen? This area under second distribution will expand. So, beta will increase, 1 minus beta, which is the area under second distribution beyond your point for alpha equal to something less than 0.05, that area will decrease. That means, power of the test, which is the ability to reject a false hypothesis, will decrease. I thought that let me also show you the table of t distribution. The table of t distribution is like this, because when you do apply t distribution in practice, you will have to find out values of t. This is shown for one tilt test. Why this one tilt test? Because the whole area of the distribution in which you will reject the null hypothesis is on the right hand side of the distribution only. You have not fixed any area toward the left hand side of the distribution, or the critical region is only on one side, critical region is not on the other side. If the critical region is either on the right hand side or on the left hand side, but not on both sides, then this is one sided or one way test. These columns, different columns are made for different values of alpha when these are the degrees of freedom. Degrees of freedom are shown from 1 to 30, 1, 2, 3 like that up to 30, and after that is written z, means for values higher than 30 you can as well use the normal distribution. Since we have been talking about 0.05 more frequently, let us see. For degrees of freedom 1, the value 6.313752 is a value such that on the right hand side of this value 6.3 is a big value. On the right hand side of 6.3 lies 5% area or 0.05, p is 0.05. As degrees of freedom increases, for degrees of freedom 30, it is 1.69, on the right of which 5% area or p equal to 0.05 lies. So, there is a fall in t value beyond which 5% area lies from 6.3 to 1.69. Z value is 1.95. Z value means value of the normal distribution beyond which 5% area lies. If you compare 0.5 with 0.1, then you see 6.3 is the value beyond which 5% area lies, and 31 for degrees of freedom 1 is the value beyond which 1% area lies. And this 31 as degrees of freedom increases, this 31 also starts reducing. There is a big reduction from degrees of freedom 1 to 2, 31.8 to 6.9, and ultimately for degrees of freedom 30, the value of t beyond which only 1% area lies is 2.45726, and below this lies the z value of the normal variate. So, there is a big fall from 31.8 to 2.45 as the degrees of freedom increases from 1 to 30. This means for say suppose your degrees of freedom in testing a hypothesis about correlation. In correlational analysis, your degrees of freedom is n minus 2, sample size minus 2. Imagine that your sample is of size 23, then n minus 2 or degrees of freedom will be 21. This is 21, and against 21 for p equal to 0.05, the value of t would be 1.720743. So, if your t value is more than 1.720743, you are going to reject the null hypothesis, and if it is for 21, if it is more than 2.5, then you are rejecting the null hypothesis at p equal to 0.01 or probability of rejection of 1%. If your value is less than 1.72 at both the level 5% and 1%, you will be accepting the null hypothesis. If your value is more than 2.5, then at both 0.1 and 0.5, you are rejecting the null hypothesis. But if your value lies between 1.72 and 2.51, then in one case, the case of p equal to 0.01, you are accepting the null hypothesis, but in another case for p equal to 0.05, you are rejecting the null hypothesis. And that means that alpha or p, I am using alpha and p interchangeably, alpha or p plays a very important role in deciding whether null hypothesis is accepted or not accepted or rejected. Now, some examples, some situations in which null hypothesis is tested by using t-test. Null hypothesis, imagine that null hypothesis is mu equal to mu 0, that the mean of the population from which a sample is drawn is mu 0. The alternative hypothesis may be mu is not equal to mu 0, or mu equal to mu 0 is the null hypothesis, and alternative hypothesis may be mu is greater than mu 0 or mu is less than mu 0. There are two possibilities for the alternative hypothesis. If the alternative hypothesis is this, then you are using two-side test. If the alternative hypothesis is either this, mu is greater than mu 0 or mu is less than mu 0, then you are using one-sided test. T in this for testing this null hypothesis mu equal to mu 0, T is defined this way: mx mean of x, mean of the sample, minus mu 0 your null hypothesis, divided by s by root n. I said that when the variance is calculated from sample itself, then you use t-test. If the variance was known, means you knew standard deviation sigma, then you could use z-test also. S is variance of the units present in the sample, and it is defined as sigma x minus mean of x whole square divided by n minus 1. Remember that in descriptive statistics, for defining variance or standard deviation, we use n in the denominator, and here we are using n minus 1. There are reasons for that, and this actually is s square, this is not s, this is s square variance, and s is the square root of this. If you take square root of this expression, then you have this s or standard deviation. Nu is degrees of freedom, and degrees of freedom is n minus 1. In this particular case, when you are testing the null hypothesis mu equal to mu 0, degrees of freedom will be sample size minus 1, t will be defined in this way, mean of the sample often in notations x bar minus mu divided by s by root n. Okay. And s square is this, square root of this is standard deviation s, which will go here. For comparison of means, you can use t-test. What is comparison of mean? Comparison of mean is that a population consists of two groups, and the difference of mean in the two groups in the population is mu 0, mu 1 mean of the first group, both are means in the population, mean of the first group minus true mean of the second group. These are true means or parameters or means of the population or universe. That difference is mu 0. The alternative hypothesis again may be that mu 1 minus mu 2 is not equal to mu 0. It may be less than 0 or it may be more than 0. It is not exactly 0. Or the alternative hypothesis may be that you must be having some idea beforehand that mean of the first group cannot be less than the mean of the second group. Then your alternative hypothesis would be that mean of the first group is higher than mean of the second group, or your alternative hypothesis may be that mean of the first group is smaller than the mean of the second group. This is the alternative hypothesis, here alternative hypothesis. In this case, t is defined like this. T is m x 1 means mean of the first sample. In some books you will find x 1 bar. If x bar refers to sample mean, then x 1 bar mean of the first sample minus x 2 bar mean of the second sample minus this difference. You are testing for this difference, that the difference between mu 1 and mu 2 is mu 0. So, that mu 0 difference divided by standard deviation of the pool data and 1 upon n 1 plus 1 upon n 2 and raised to power half. What actually it means that if the two samples are independent, the variances of the samples separately are s square by n 1 and s square by n 2, and variance of the difference would be s square by n 1 plus s square by n 2, and square root of that is s, and root 1 upon n 1 plus 1 upon n 2. This is s is square root of sigma n 1 minus 1 s 1 square plus n 2 minus 1 s 2 square divided by degrees of freedom, or n 1 plus n 2 minus 2. N 1 plus n 2 minus 2 is the degrees of freedom of the data. So, if first sample consists of 20 observations and second sample consists of 25 observations, then 20 plus 25 45 minus 2 degrees of freedom will be 43, and for 43 you can as well use the Z test, because the value of t for degrees of freedom more than 30 will be same as of standard normal distribution. For method of paired comparison, one by one, when an experiment is so conducted that each observation in one sample is paired with a value from the second sample, control and experimental group, before and after type. Before performing, you may have the same sample, and for each respondent or each subject, you have one reading before conducting the experiment and second reading after conducting the experiment, or you can have control and experimental groups, and you are comparing whether experiment makes any difference. The null hypothesis would be that experiment does not produce any difference. That means, there is no difference in the mean in the experimental group and in the control group, or before and after type. The alternative hypothesis again can be of two types. One, that the difference is not 0, that there is a certain difference, and this difference can be negative or positive. After the experiment, the values may have improved or deteriorated. The alternative hypothesis can also be that mu d is greater than 0 or mu d is less than 0. Direction is specified now. And this shows that actually review of literature or overall understanding of the experiment is also very important, because you are going to decide on the basis of review of literature whether you should go for this alternative hypothesis or one of these two alternative hypotheses. Depending on the values, or depending on whether you go for one side test, this is one side test when alternative hypothesis is defined like this, or you go for two side test, this is two side, this is the condition for two side test. Depending on whether you go for one side test or two side test, you will have critical region on one side or both the sides, and therefore, the t values with which you will compare your calculated value of t will differ. For paired comparison, you can use this formula also, t equal to mean of the difference minus hypothesized difference divided by S divided by root n. Here S is sigma, actually this is S square. S square is sigma d minus m d whole square. D is the empirical difference and m d is the mean difference. So, difference for ith pair, mean difference for overall sample, whole square divided by n minus 1. This is the formula for variance of d. So, this is variance of d. Here we should write S square, and S is the square root of this whole thing, that is standard deviation, or that is standard error of m d minus mu d. Degrees of freedom is n minus 1, because you are having n observations on pairs of observations, control and experimental. T test is also used for testing correlation coefficient. We have covered this in lecture on correlation coefficient, that once a correlation coefficient has been calculated, we would like to know whether this correlation is statistically significant or not. And as usual, the meaning of significance is that we want to know whether this correlation can come due to sampling fluctuations from a population in which actually the two variables are not correlated, they are independent. If a particular value of correlation from the sample comes or can come due to sampling fluctuations from a population in which the two variables are actually uncorrelated, we say that this correlation is insignificant. But if this null hypothesis of correlation being insignificant or correlation in the population being 0 is rejected, then we say that the correlation is statistically significant. A small value of correlation may be significant at 0.05 and a slightly bigger value of correlation will be significant at 0.01 double star, and a still higher value of correlation would be significant at 0.001, 1 in 1000, p or alpha being 1 in 1000, single star, double star, triple star. The degrees of freedom for this t is n minus 2, the sample size minus 2. So, we calculate t, we identify degrees of freedom, choose the appropriate row of the t distribution for this degrees of freedom, identify the value for 0.05 or 0.01 or 0.001 and compare our calculated value of t with the tabulated value of t. If calculated value is less, we accept the null hypothesis, and if calculated value is more, we reject the null hypothesis. Null hypothesis is that rho equal to 0. The value of correlation between two variables in the population from which a sample has been drawn is 0, means the variables are uncorrelated. Actually, this idea of sampling fluctuation is better shown by this figure. If a correlation, imagine that there is a population in which two variables are uncorrelated, means correlation is 0, this is correlation equal to 0. Then in the sample you can get 0, you can get a small negative number, a still a smaller negative number like this. All these are possible values and their probabilities can be decided by looking at this probability density function of sample correlation. This is the density function of sample correlation when in the population correlation is 0. When in the population correlation is less than 0, we move towards this side, then the distribution of sample correlation moves towards this kind of density function. Notice that this distribution is positively skewed. If the correlation coefficient is positive and more than 0, then the distribution is like this. And notice that this distribution is negatively skewed. So, you see in testing a null hypothesis regarding correlation, we look for whether it is possible to get a particular sample correlation under this distribution or other distributions under alternative hypothesis. There will be fluctuations in the sample correlation. Sample correlation cannot be same as in the parent population. The t-test is also used for testing significance of regression. So, when you apply regression analysis, you may apply bivariate regression or you may apply multiple regression. Bivariate regression when you have only one independent variable, multiple regression when you have several independent variables. In the second case, you will have several partial regression coefficients. And however, in each case the null hypothesis will be beta equal to 0. This beta equal to 0 will mean that the value of partial regression coefficient if you conduct regression in the entire population, it will be 0. That means, that particular variable, the only variable in bivariate, or one particular variable in multiple regression analysis, independent variable, has no effect on the dependent variable, beta equal to 0. And as in case of mean and differences and correlation, here also the alternative hypothesis can be that beta is not equal to 0, beta is less than 0 or more than 0. Less than 0 or more than 0 will mean that that variable affects the dependent variable. If beta is less than 0, it simply means that the relationship is negative, and if beta is more than 0, it means that relationship is positive. So, this is shown here that alternative hypothesis can be this or this. If the alternative hypothesis is this, we go for two side test, and if alternative hypothesis is one of them, then we go for one side test. And the formula for T is B minus 0, this 0 is beta actually. Partial regression coefficient or simply regression coefficient in the population, and divided by standard error of B. Standard error of B, I have not given the formula, but computer output will give you the value of T and standard error and P directly. You must understand the logic behind application of this. You do not have to calculate manually yourself the values of T and standard error and P or alpha. Example of mean. I thought that let me give some examples also. This is the example of mean. This is the sample 4, 8, 12, 6, 42, 9. Mean is 12.78, standard deviation is 14.25, and the value of T is 12.78 mean minus 10 hypothesized mean, whole thing divided by 14.25, this S, and divided by square root of 9. 9 is how many values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 9 values. So, square root of 9. You get T value of 0.58. Now, tabulated value of T for level of significance of 0.05 and degrees of freedom 8 is 2.30. It will be better if here also you write 9 minus 8 square root of 8. And however, this for degrees of freedom 8, this value beyond which 5% area lies is 2.30. Since 0.58 your calculated value of T is less than the tabulated value of T 2.30, the null hypothesis is not rejected. For alternative hypothesis that mu is greater than 10, however, we have to take T at 0.05 as 1.860, even then the null hypothesis will not be rejected. This is the example of comparison of means mu 1 minus mu 2, same logic, similar formulae, sample 1, sample 2, means, S square of the pool data, S, T, and comparing this T value 0.0045 with tabulated values in two side test, in one side test. This is example of paired comparison. These are the observations on one group, observations on another group, may be control, experimental, D difference, then T for difference, MD mean of difference minus hypothesized mean, which will be 0, S by root n, S is square root of this whole thing, because this thing sigma, remember that sigma differences square divided by degrees of freedom is defined as S square, and square root of this actually should be S. This S without square root, this S should be read as S square. So, T is minus 0.458, degrees of freedom 9, T 9 is 2.26. So, what is the inference? Inference is that because this is less than this, means 0.458 will be compared with minus 2.26. This is more towards 0 than this. So, algebraically this 0.458 with minus sign is a bigger figure than minus 2.26, and therefore, null hypothesis is accepted. For proportion, similarly, the standard error of proportion is square root of p q by n, otherwise all calculations and logic are similar. For comparison of proportions, same thing, two samples p 1 minus p 2 is the observed difference in proportions. These are standard errors of different groups. We add them to get standard error. P 1 q 1 by n 1 is variance of p in the first sample, this is variance of p in the second sample, and variance of the difference is sum of these two, and standard error is the square root of this. Degrees of freedom is n 1 plus n 2 minus 2. T is used as part of median test. If you remember a lecture on hypothesis testing, then T was used as a part of median test also. Here is an example, I do not have to discuss this example again. Example of correlation. If you have the same correlation for a bigger sample, then you will find that it can be now significant, if in the previous case it was not significant. So, whether a correlation is significant or insignificant depends on sample size also. For a smaller sample, it can be insignificant, but the same correlation for a bigger sample may be significant. Logic suggests that a small sample may be an extreme sample, and so this. Nowadays, in place of saying whether this t value is significant or not, we actually calculate p value, the area which will lie beyond calculated value of t, that is called p, and if p is less than 0.5, reject the null hypothesis is rejected, or you can choose 0.01 the value of p and then reject the null hypothesis if p is less than 0.01, single star, double star, or you can compare it with 0.001 triple star. An example, this will be the computer output for regression multiple regression analysis. B is standard error, beta, T significance. I have already discussed this issue. So, T is also linked with regression with analysis of variance. We will discuss analysis of variance in the next lecture, and we use F, but for this F is analysis of variance is used when you are comparing 3 or more groups. After finding that 3 or more groups differ, you would like to know from which pair of groups more difference comes. So, you can use t test there, pair wise you use t test, and for all the groups together you use F test. So, actually t test has wide applicability. It is not only used for testing whether mean of the population is this, or difference in means of two subgroups is this, or correlation is this, is correlation statistically significant, or it has appeared when you have numbers and you calculate correlation, some correlation will come, but the issue is whether such correlation can come even when in the parent population two variables are uncorrelated. T-test has been used for testing significance of regression coefficients also, and in multiple regression analysis for testing significance of several partial regression coefficients. The next technique we will discuss will be of ANOVA, analysis of variance. Analysis of variance is used when there are 3 or more groups and you want to see whether they are different. But after performing analysis of variance, you can apply t-test for comparing two groups at one point of time, and there is a relationship between the two, as the previous slide shows that t square is f. So, there is a relationship between t and f. We can make use of that equation in certain conditions. Thank you.